Hi everyone. I decided to make another video. Why? Because I did not manage to solve two problems in my recitation classes. And I've heard that some other instructors also did not manage to solve those problems. But since you need them to do your homework, so I decided to make this video. So let's start. First, let me explain the situation. Let's imagine this problem is not from this book. I took it from some other book. I don't remember which one. Let's imagine this situation. So we have a rigid object, this ruler, right, or some rod, right? And the axis of rotation is over here. So this rod can swing around this axis of rotation. Right? So first, initial situation. Yeah, of course, the length of the rod is given, the mass of the rod is given, and first initial conditions. I'm holding this ruler, and then I will release it. So if I release it, of course, it will start experiencing rotational motion. So we need to find the angular velocity of this rod when it swings all the way down to the vertical direction. So we need to find angular velocity at this point. Right? So let's do it. First, of course, I will make a picture. And then I will write what is given, and then we will start discussing it. So I'll just put a new bullet, right? And so here is my corner. Okay, this is kind of wall, right? Here is my hinge, right? And here is my ruler, or the rod, piece of rod. Right. Okay, so that is the rod of length L. Okay, length L and mass M. Okay, let me write what is given. Length is 1.5 meters. And let me write it here. Length is 1.5 meters. Mass is, I don't remember, what is mass? 8 kilograms. Mass is 8 kilograms. And what else? That is my initial position, right? So that is my initial, no, let me label it as position 1. That is my position 1. And then, of course, this ruler will experience circular motion, and it will end up over here. So let me now draw our second position of this ruler, slightly distorted. Again, this length is L, right? And this will be my second position. This will be my second position. Okay, I think I gave almost everything. Now let me write what will be the initial angular velocity. Since ruler is at rest at the first position, of course, initial angular velocity is 0. And what do we have to find? We need to find angular velocity at this final point, omega 2, and I will put a question mark. And what are we going to use to solve this problem? We're going to use conservation of mechanical energy. We assume that there is no friction. We can easily neglect air resistance, and force of gravity, which acts on this ruler, is the conservative force. We can introduce potential energy, and we can use conservation of mechanical energy. So let me write. So we're going to use conservation of mechanical energy. So I can write E at point 1 must be equal to the total mechanical energy at point 2. My initial point in the solution. Now, of course, we need to write explicitly what is inside of this total mechanical energy. Right? Of course, I can write that we have kinetic energy of the rod plus potential energy of the rod throughout this motion. So I can write K initial plus U initial equals to K final plus U final at the point 2. Now we need to understand which kinetic energy expression for the kinetic energy we can use. Now we don't have a translational motion. Now This motion is not translational. This is the pure rotational motion of the rod around this axis of rotation. So, if you remember how to, of course, we derived the expression for the kinetic energy, rotational kinetic energy, right? In our lecture. How to restore that expression for the rotational kinetic energy if you remember translational kinetic energy. Most of students remember that. So if you remember, K translational equals 1 over 2 mv squared. Now let's, using this, let's write down the expression for the kinetic energy, rotational kinetic energy. So we need to replace these translational quantities with rotational quantities. So first replacement. Instead of mass, we have to use the rotational equivalent of the mass, which is the moment of inertia. We discussed it in the previous recitation classes, discussed enough. And then what? Instead of translational velocity, we have to use the angular velocity. Okay, so if you replace these things, these quantities, you can write immediately the expression for the rotational kinetic energy. So I can write K rotational equals 1 over 2 moment of inertia times square of the angular velocity. So that's what we're going to use over here and over there. So let me circle it. Just ingredients for this equation. Right? I'm just preparing ingredients for this equation. Now we need to understand how can we find potential energy due to gravity. And here's the problem with that potential energy. And we did not discuss this in our lectures. How to find a potential energy of a solid body, rigid object, rigid body. What is the problem? So far, we used potential energy due to gravity, but we use potential energy of a point mass. So if you have one point, right, and if you have a reference level, we could write easily gravitational potential energy by using the expression mass times acceleration due to gravity times the distance from the reference level to the point where the mass is. Now the problem is this. You have a rigid object, and force of gravity acts on all points. All points. This point, this point, this point, this point. We have a gazillion number of point masses. And each of those point masses give a small contribution to the total potential energy. So there will be some contribution from here, from there, from all points. So now the question, if you add them all up, what are you going to end up with? Right? Because now it's not a point mass. Now it's a rigid object, tons of points connected together rigidly. Right? And again, I did not discuss this trick in the lecture. So the trick is this. We have to use the beauty of the center of mass. Center of mass has a few remarkable features, and this is one of them. So the trick is, what do you have to do in order to find the potential energy due to gravity of a rigid object? Find the center of mass. Okay, let me draw it. Find the center of mass of a rigid object. For example, this is here, because we have symmetrical object, so the center of mass is at the center. Then imagine, sort of squeeze the whole object into a point. Of course, it's imaginary, right? Squeeze the whole object into a point mass positioned at the center of mass. So the total mass of a rigid object now will be positioned at the center of mass. So basically create like a fictitious point mass. Of course, it's all imaginary, right? So you squeeze the whole object into the point at the center of mass, and then draw your, and then you can find a potential energy of this point mass relative to some reference point, whatever reference point you pick. Now let me explain it here on the board. So let me put it like this. U gravity, and I will put question mark. So if you have a rigid object, right? And you want to find potential energy of this rigid object. Let's say you pick a reference level, you get, let's say this is UG equals 0, right? This is your reference level. Right. So idea is you find the center of mass point over here, let's say, and then now instead of this rigid object, you have to deal with this situation. So you will just, at the point of center of mass, you will, okay, let's say the mass of the object is m. You create a fake particle with a total mass m, positioned at the center of mass, right? So this point is this point. The same reference level, of course, right? And now you just need to use this distance. Let's say ycm. Distance from the reference level to the point where your center of mass is. The same trick we used to calculate torque due to gravity in our previous lecture. It's exactly the same idea. We just need to use the beauty of the center of mass. So that's what we're going to use here. U equals, okay, so U due to gravity over rigid object, over rigid solid object, will be equal mg, where m is the total mass of the object, and times y of the center of mass. Okay. So that's another ingredient for our conservation of mechanical energy. So let me frame this now. So we have these two ingredients which will go into our conservation of mechanical energy. So we're almost done. So now we just need to plug them, apply conditions, and see maybe this equation will be enough to solve the problem. So now let me separate it like this. My board is small, but I wish I had a little bit bigger board. So now I will continue this line. So let me, okay, this arm will go to this point. So K1, 1 over 2, moment of inertia times omega squared. 1 over 2 I omega 1 squared. Of course, omega 1, it's an angular velocity at point 1. Then, potential energy. Okay, now, of course, I haven't picked the reference level. So let me pick the reference level, for example, over here. So let's say this is my reference level, U equals 0. Right. That will be my reference level. Okay, and what? Now, this is point 1. This is point 1. The center of mass is over here, so we have to use this trick. Right? So this is the center of mass. So now we have to imagine that instead of having a rigid object, okay, this rigid object, we have a point mass, right, at position at the center of mass, and the whole mass is over there. Right? So and mg times distance from the reference level to the point where the center of mass is. And of course, in this case, it's 0 because center of mass lies at the reference level. So potential energy at the initial point 1 is 0. But anyway, I will write it plus mg y cm, and let me put it subscript over here 1. And now let me dump immediately these terms. Okay, as I told you, this is 0 because it is at the reference level. And we also know that initial angular velocity is 0, so we can dump this term as well. So the left-hand side of our equation is 0. Now we need to take care of the right-hand side. So let's do it. K2, 1 over 2 moment of inertia times omega 2 squared. Right? And now potential energy. The center of mass, of course, will go, and it will be here at the center, right? So that's my center of mass. So in order to find potential energy of the rigid object in the position 2, I need to use y sub cm. It's this distance from the reference level, this is my reference level, to the position of the center of mass. So this will be my y cm, at point 2. And of course, since length L is the same over here, right? So y sub cm equals to L over 2. So I will write here, and this potential energy, of course, will be negative because our object now, our center of mass, is below the reference level. So I will put minus mg. First I will write y sub cm at point 2. This is 0, and here we have these two terms. Now we need to say a few words about the moment of inertia. This is a rigid object. We know how to calculate moment of inertia over point mass. It's quite simple. You just take mass and multiply by the square of the distance from the axis of rotation to the point where the mass is. But if you have a rigid object, calculations of the center of, calculations of the moment of inertia is not simple. You have to pass calculus 3 in order to do that mathematically. We're going to use table 12.2 in your book, right? Just go to table 12.2 and use that. And I will probably write, but be careful. You have to use the proper expression. There are two expressions for the moment of inertia of a rigid object. Of this, of the rod. So there is one when the axis of rotation goes through the center of mass, and the second expression when the axis of rotation goes through the end. So of course we have to use the moment of inertia when the axis of rotation goes through this end. Okay, and I will write, so the moment of inertia equals to, I think it's 1 over 3, ml squared. 1 over 3 ml squared, right? Okay, now let me write it. It's a table 12.2. So I found, I used the expression, I used table 12.2 to find this expression. It can be calculated mathematically, I can do it, but it's problem not for this level. So now let's write it all down. I will probably take this term, move to the to the left hand side with plus, and instead of y sub cm, I will use L over 2. Right? So as a result, it will be mg L over 2 equals, and this term I will leave on that side. It's 1 over 2 I omega 2 squared. Right. First of all, 1 over 2 gets cancelled. And what do we have to find? We have to find this. This is our unknown. Mass is given, acceleration due to gravity all the time we know, L also given, and moment of inertia, mass is given, length is given. So pretty much we know everything except 1 omega 2. So one equation, one unknown, problem is almost solved. So let's just solve it for omega 2. So of course, omega 2 will be square root. Moment of inertia goes downstairs in the denominator, and we will have mgl divided by the moment of inertia. And so now let me plug the expression for the moment of inertia. I will get square root of mgl divided by 1 over 3 ml squared. Okay, this is L. One L gets cancelled. This goes, and 1 in the power mass. Actually, we don't need mass, it looks like. So as a result, we have square root of 3g, and one of these L's survived. 3g divided by L. So that is the answer. Okay, let me write it underneath and also write down the answer. So omega 2 equals square root of 3g divided by L. And let me use my notes in order to write the answer. Approximately 4.43 radians per second. Let me frame it. That's the answer, and that's the expression for the answer. Again, the major point of this problem is how to find potential energy over gravitational potential energy of a solid object, and the second application of this expression. Although we used in one problem this expression in our recitation class. Okay, that is the first problem. Now we need to look at the second problem. Okay, this problem which we just solved, this should be very useful when you start solving problem 1274 from your homework. But in order to make this problem ridiculously useful, I decided to add additional question or additional part to this problem. So which part? Okay, let's take this end of this rod, this ruler. Of course, this point experiencing a pure circular motion, pure rotational motion, right? So you remember rotational kinematics, which we discussed like a couple of months ago. If you have a point which experiencing a pure circular motion, we can describe that motion using two sets of quantities. You can describe it using angular quantities. For example, you can use angle, you can use angular velocity and angular acceleration, right? But also you can use linear quantities, tangential quantities. We can use arc length, tangential velocity, and tangential acceleration. So now we have this point, and we know the angular quantity, right, which describes how fast angle changes in time at this point too. So now let's add additional question. What will be the tangential velocity of this end of this rod at this point too? So let's just find tangential velocity, right? Again, it will be useful in your problem 1274. I need to erase something. I will need these numbers. Let me erase this part. My board again is a little bit smaller than I would like to have, right? So I can erase this as well. So let's start. No, first let's recall the relationships between these angular quantities and tangential quantities. Usually you guys tend to forget this relationship quite fast. Let me remind you. So, the arc length, all right, equals to radius times the angular, times angle, right? And of course, this angle is in radians, must be in radians. That is basically definition of radians. You remember we defined angle in radians as the ratio of arc length divided by the radius if you have circular motion. So if you have circular motion, let me draw a small circle, right? So let's say this is the angle theta, and this is arc length s. Right? Then, in order to find the relationship between tangential velocity and angular velocity, you just need to take first derivative of this expression. So you need to differentiate with respect to time, and you will get v tangential equals r angular velocity. And of course, it's very important, angular velocity must be in radians per second, because that's what we differentiate, and this angle is in theta. So again, let me use a green, or blue. It must be in radians per second. It's very important. And then if you differentiate with respect to time one more time, you will get that tangential acceleration equals r. And again, r is fixed because particle moves around the circle, so r is constant, times alpha, angular acceleration. And again, this angular acceleration must be in radians per square second. But what we need in order to find tangential velocity, we need to use this. That's what we need to use. So, and after that, it's just basically you need to plug numbers. So, but anyway, let's do it. So V tangential, let me write at point 2, because we want to find tangential velocity at this point at the end of the rod and at the point 2 equals, what is a radius in this case? What is r in our case? So this point moves around this circle. Right. So the radius is the total length of this rod. So I will put L times, and of course angular velocity, which we just found, this, right? Angular velocity, omega 2. So now we just need to plug numbers, and of course we will end up with L is 1.5 meters times angular velocity at point 2 we just found, 4.43 radians per second. So if you multiply it, you will get, let me look at my notes, 6.65. 6.65 units. You remember, radians, there is nothing behind radians. It just reminds you, hey, don't forget that this is angle. But actually inside of radians there is nothing. It's just an empty box. Like degrees, radians, right? It just reminds us that angle is measured. But again, behind this there is nothing. So it will be 6.65 meters a second. So that's tangential velocity of this point, this end at the point 2. So this will be my V tangential at point 2. Okay, so, and of course, this problem should be useful for the problem 1274. In your homework, this problem should be useful to solve problem 1274. Okay, it should be enough.